Hello students, in the previous class I explained that what are the different types of measuring instruments, the basic types, that is the primary and secondary types, and also I explained that how the torque is produced, that is the deflecting torque, damping torque, controlling torque. So how exactly these torques we are going to consider, that is the basic principle, and also how exactly it is generated in the different parts of the instrument that I explained. Today we will see that the constructional features and working principle of dynamometer type wattmeter and the induction type energy meter. Okay, as the name indicates, you see that the wattmeter, the watt is the unit of power. You are going to use this dynamometer type wattmeter to measure the power. Okay, before going in detail with this the dynamometer type wattmeter and the induction type energy meter, I will explain to you how exactly we are going to measure the current, voltage, and then in terms of this power we are going to express in terms of voltage and current, how exactly we are going to consider that, and then how that energy is expressed in terms of power. Okay, now you see that the current, when you are going to consider, it is expressed in terms of amperes. Voltage we are expressing in terms of volts. Power is the product of voltage and current in case of DC. So this you are going to express in terms of, that is volt ampere. In case of AC, it is VI cos phi. So you are going to express in terms of watts. So energy is the total power consumed in particular time is the energy. That is why you are going to consider it is VI cos phi. This whole thing multiplied by T is the energy consumed in particular circuit. Okay. So these are the concepts you are considering for current, voltage, power and energy. When we are going to consider the measuring instruments, we have to construct the first the current coil and the voltage coil. Okay. Current coil, how exactly we are constructing it? We are going to consider only few turns, means the length is less, okay, our thickness is more. So you are going to use a thick few turns wire or coil to construct this current coil, because when we are going to consider the concept, so current I is equal to V divided by R. In terms of dimensional parameters, R we are going to represent it is rho L by A. When the area of the coil is more, the resistance will be less. So when the length of the coil is less, the resistance will be less. To current to flow properly, so the resistance should be less. Under that condition, the current will be more. That's why we are going to use for a current coil the few number of turns of thick wire. For voltage, we are going to use the thin coil with more number of turns. Why? Here when we are going to consider this, V is equal to I into R. To get that proper voltage, R should be more. How exactly we are getting this R, that is the increased value? Since A is less, the R will be more. Since the length is more, the R will be more. Since V is directly proportional to resistance, we are going to use, that is thin coil of more number of turns for voltmeter coil. So for current coil, since the current is inversely proportional to resistance, we are going to use the thick coil of few number of turns. So here the current can flow easily in this. Now that is why you are going to use, that is I is inversely proportional to R relationship to manufacture or to connect the current coil. Okay. So now the power is the product of voltage and current. Now you have to use both current coil and voltage coil. How exactly you are using both current coil and voltage coil? in case of wattmeter. You see now how exactly I am going to connect. Here the supply is given, this is the supply to the circuit, and then you are connecting a load to this. When you are measuring a voltage, so now I told you that you have to use that thin coil, and when you are measuring current you have to use that thick coil. Thick coil we are going to represent with only few turns, because here the length of the coil should be less. So now you are going to represent, this is the voltage coil. Since the resistance is more, you are going to represent with the resistance. The terminals you are going to consider it is MC, and then this is V. So the voltage coil you have connected across the load, and the current coil you have connected in series with the load, because through this current coil you are going to measure what is the current flowing through the load. Since you have connected this voltage coil across this, the voltage across the load is same as the voltage across the current coil. In turn, you can measure the power that is consumed by this load by considering the current flowing through this current coil and voltage across this current coil, that is P is equal to V into I. Now you see that how exactly this wattmeter works, how the torques are developed in case of this wattmeter. So how exactly it is going to measure power in case of this DC circuit and power in case of this AC circuit. Then we will go to this energy. So that is, we are using this induction type energy meter to measure the energy, that is the power consumed multiplied by time. Okay. Since we are using this power and time, since we are using, and also we are using this to measure this power, current coil and this potential coil, you see that how exactly we have constructed this energy meter, how it works in the later stage. First we will consider this measurement of power by using dynamometer type wattmeter. The dynamometer type wattmeter works on very simple principle, and this principle can be stated as, when any current carrying conductor is placed in a magnetic field, it experiences a mechanical force, and due to this mechanical force deflection of conductor takes place. You see that how exactly we are considering. This is what I had written on the board. See here, the supply is given to this, the current coil of few turns you are going to connect in series with the load to measure the current flowing through the load, and pressure coil of more number of turns and thin coil you are going to connect across the load to measure the voltage across this, and to limit the current flowing through this you are going to connect a series resistance with this. Okay. So now you see that here how exactly the current coil and pressure coil is connected in the construction feature of dynamometer type wattmeter. See here, the current coil we have divided into two halves. This is the fixed coil. The current coil is the fixed coil. It is connected in series with the load. Okay. So across this source, see that the current coil is connected in series with the load, and the voltage coil is connected to the movable part, that is the pointer. Okay. And also here it is connected across the load. You see that it is connected to this one terminal of the supply, and then here it is connected across the load. So the current, this resistance R is used to limit the current flowing through this potential coil. Okay. Here the pointer is mounted on the spindle. Here it is going to show the deflection on this particular uniform scale. Okay. This is the construction of dynamometer type wattmeter, that is explained in this. So it has two types of coils, moving coil and the fixed coil. Moving coil is the potential coil or pressure coil, this fixed coil is the current coil. Okay. The moving coil moves the pointer with the help of spring control instrument. Here it is attached to that spring in this. Okay. So if you are not using the spring, in the last class I explained that, so the deflecting torque you have to balance with this, the torque produced due to this force on this spring. That's why, so when you are going to consider the TD is equal to Tc, you are going to get that equilibrium condition. So that is the steady state condition. Under that condition you will get the proper reading. So that is the pointer will move on this scale. A limited amount of current flows through the moving coil so as to avoid heating. To avoid this heating, you are going to connect a series resistor, high value of series resistor, to avoid the current. So if it is the current increases in this, the heat will also increase. To avoid that one, you are going to connect high value of resistor in series with the moving coil. The moving is air cored and is mounted on a pivoted spindle. In the last class I explained how exactly it is connected to the spindle. Okay. So the one end of the spring is fixed to the spindle, another end is thus movable. Okay. It is pivoted spindle, this spring is attached to the pivoted spindle and can move freely. The electrodynamometer type wattmeter, that is moving coil, works as a pressure coil, because since it is, and also we are going to call it as a potential coil because it is going to measure the voltage. Moving coil is connected across the load, thus the current flowing through this coil is always proportional to the voltage. Now you see that fixed coil is connected in series with the load. So here you are going to use to measure the current flowing through the load. So how exactly you are going to connect? It is connected into, that is divided into two halves and connected in series. You see that the current coil is divided into two halves and connected in series. So it will give that considerable amount of electric current. So it is called it as current coils. In the previous type of that is electrodynamometer type wattmeter, so the current measured by those meters was about 100 amperes. Now in case of this modern wattmeter, these are designed to carry the current about 20 amperes in order to save the power. So this is the construction of the moving coil and fixed coil. So next we have that due to this deflection, that deflecting torque produced, here you see that current coil is connected in series. No, here the current I1, I2 will flow in this. What will happen here? Since the current I2 is flowing, the flux Phi2 will be produced, and due to this current I1 flowing through the pressure coil, the flux Phi1 will be produced. Due to the interaction of this Phi1 and Phi2, the deflecting torque will be produced. I already told you that if you are not going to control this deflection properly through this spring torque or controlling torque, so we will get this error. So that's why we are using this control system. So you can use that gravity control or speed control. Usually we are going to use speed spring control in case of this wattmeters, okay, because the gravity control system cannot be employed because they have appreciable amount of errors. I explained both the types in the last class, that is gravity control and spring control. In this particular case, we are going to use this spring control. And one more thing, that is we have to produce this damping torque. It has to, that deflecting torque also has to overcome this damping torque. How exactly you are going to create this damping system? You see that here we are using that air friction damping. So in the last class I explained air friction damping, eddy current damping, and then fluid friction damping. Here we are particularly selecting this air friction damping, as eddy current damping will distort the weak operating magnetic field. That's why we are going to use this air friction damping. The scale is uniform. This whatever you are using here, the scaling system, that is uniform. As moving coil moves linearly over a range of 40 degrees to 50 degree on either sides. So now you see that how exactly this dynamometer type wattmeter works. I already told you, you consider this is the applied voltage V, okay, current flowing through the current coil I2 and current flowing through the pressure coil I1. So now due to the interaction of the flux produced in both the coils, the torque will be produced. So here we are considering V is the supply voltage, I is the load current, and then R is the resistance of the moving coil that is connected in series with the moving coil. Then current through the fixed coil we have considered it is I of F. So current through the moving coil we have considered it is I of m. So that is equal to V by R, because you see that we have considered, what is the symbol we have considered for current flowing through the load? We have considered this is small letter I, and then current flowing through this we have considered it is I of f. See now here, since this voltage coil is connected exactly across the load, since the voltage across this is V divided by R, the total resistance R. Here to avoid the current, you are going to connect the resistor R, and this is of the potential coil, the total resistance you are going to consider, that will be that V by R is equal to current flowing through this particular that moving coil. Since it is a moving coil, we will use that symbol M to make you understand better. So current flowing through the moving coil, that is equal to V divided by R, because the total voltage across this pressure coil or potential coil is V, the total resistance is R. So the current flowing through this moving coil, that is I of m is equal to R. Then current flowing through this load, so you are going to consider as I. Now the flux produced due to this and the flux produced due to this, due to the interaction of these two, the torque will be produced. So you symbolize this is phi 1 or phi 2, this if you are symbolizing this is phi 1, you symbolize this is phi 2, okay. So that is why, so here Td, the deflecting torque, is directly proportional to the current flowing through the load and also the current flowing through the moving coil, that is directly proportional to IV. This is current flowing through the moving coil, we have considered V by R, current flowing through the load we have considered I. When you are substituting this Td is directly proportional to IV divided by R. You see that, what is this Vi? Vi is the product of voltage and current, this represents the power. For a DC circuit, the deflecting torque is proportional to the power, because this Td is directly proportional to IV. The value of resistance is the fixed value, that is why you can consider this Td is directly proportional to the product of voltage and current, this is nothing but the power. So now deflecting torque is directly proportional to the power. For any circuit with fluctuating torque, the instantaneous torque, when exactly you are going to consider that instantaneous? It is in case of AC circuit, okay. So because in case of AC circuit, the voltage and current both will vary sinusoidally like this, okay. When you are going to consider V is the reference, V of t, that is equal to Vm sin omega t. So current, this will be, that is Im sin omega t with the angle you are going to consider plus or minus phi, depending on the inductive circuit and capacitive circuit. In case of inductive circuit, current lags the voltage by an angle phi. In case of capacitive circuit, current leads the voltage by an angle phi. So this is how you are going to represent. So in this case, you can measure the instantaneous voltage, and this torque will be produced due to the voltage and current. That is because here the current flowing through this is directly proportional to the voltage. So the flux produced in the pressure coil, the current flowing through the pressure coil, and the flux produced due to the current flowing through the current coil will produce the torque. Since both voltage and current are instantaneous, the torque will also be instantaneous. So here for any circuit with fluctuating torque, the instantaneous torque is proportional to instantaneous power, because power is the product of voltage and current. In this case, due to inertia of moving parts, the deflecting torque will be proportional to average power. So for sinusoidal alternating quantities, we know that the average power is Vi cos phi, where V is the RMS value of the voltage, I is the RMS value of current, and phi is the phase angle between the voltage and current. So this is how you are going to measure the power in case of both DC and AC circuits. So you are going to use this dynamometer type wattmeter to get the power in case of AC and also in DC, whether it may be AC or DC, irrespective of the fact whatever it is going to connect, that is to the AC circuit or to the DC circuit. So what are the ranges you are considering? Usually the current circuit, the 0.25 ampere to 100 ampere with employing current transformers. Without employing this potential transformers, you have for potential circuit 5 volts to 750 volts. Now, you see what are the advantages? Here I already told the scale is uniform up to a certain limit, and they can be used to measure AC as well as DC quantities, as scale is calibrated for both. So, these are the errors you can consider. Errors in the pressure coil inductance, errors may be due to pressure coil capacitance, errors may be due to mutual inductance effects, errors may be due to connections. So, you have to connect that properly, the current coil and pressure coil, otherwise you will get the error. Then error due to eddy currents, errors caused by vibration of moving system, then temperature error, errors due to stray magnetic fields. So, you have to take care of these errors when you are constructing the electrodynamometer type wattmeter. Before going to the single phase induction type energy meter, I will show you how exactly the wattmeter looks like. So, this is the wattmeter. I have brought the wattmeter, that is unity power factor wattmeter. Since here you are considering the term VI cos phi, this cos phi represents the power factor. You can't expect always this cos phi is equal to 1. When the load is resistive, you are going to get this cos phi is equal to 1. Means the voltage and current both are in phase with each other. Under that condition, phi is equal to 0, cos 0 is equal to 1. When the load is inductive and capacitive, you won't get this cos phi is equal to 1. Under that condition, you are going to use that low power factor, that is LPF wattmeter. Okay. Here we have the connections, that is one is the current coil connection, another one is the voltage coil connection. This current coil is connected in series with the load, voltage coil is connected across the load. So, here that is why we have represented this is M. So, this main and load. So, this M represents main and this L represents the load. Here you can consider that is C and here it is the V. This C represents the common terminal for the current coil and the voltage coil, and this V represents, that is a voltage terminal. Okay. So, here M, L, C, V you have. This V may be variable if you are using the same wattmeter for different voltage ratings. So, you can use the different voltage connections here. Okay. So, this can be used for, so here for different voltage ratings you can use. See the scale in this, here the scale of the wattmeter is uniform. I already told you this deflection. So, it will be from initial position to final position with the degree of 40 degree to 50 degree, it will maintain that uniform scale. Uniform scale means this 0 to 500 and then 500 to 1000 to 1500, it is a uniform scale it is. Otherwise, this scale will vary. So, that is why we are going to call it as a uniform scale. So, this is how we are going to measure the power by using this wattmeter. Wattmeter, you can use that unity power factor wattmeter and LPF wattmeter, that is low power factor wattmeter. When the load is inductive and capacitive, you are going to use LPF. When the load is resistive, you are going to use this UPF. Okay. So, this has the 4 terminals: main, load, common and then voltage. Voltage ratings, the different voltage ratings you can connect. Okay. So, this is how the dynamometer type wattmeter works for the measurement of power. Now, we will move on to this energy. Here also you will have both current coil and pressure coil, but the energy is here you are going to consider, that is power consumed in particular time. Since power in AC circuit is VI cos phi, that multiplied by time will give you the energy consumed. So, these type of energy meters you are going to use in the domestic purpose. So, here this is how the construction of this energy meter is there. See here the voltage coil you have, here you have that current coil. Okay. There are 2 coils you have mainly, that is current coil and voltage coil, as in the case of dynamometer type wattmeter. So, these 2 you are going to use to measure the power. Now, power multiplied by the time. What is the time you are considering? You see in the working principle. Okay. The single phase induction type energy meter, is also popularly known as watt hour meter, because it is power consumed in particular time. Since you are considering, it is also called it as watt hour meter. See here, the one more thing we have introduced in this, we have this rotating aluminum disc. This is of light weight. So, it is connected to this spindle and the spindle is attached to this gear system. Okay. Here we have that magnetic brake and we have this copper shading ring. So, what is the function of this copper shading ring? So, what we are doing is, we are using as usual what I explained in the dynamometer type wattmeter, we are going to use this thick wire of few turns to this current coil, thin wire of more number of turns to this voltage coil. This voltage coil is arranged in such a way that it should have that high inductive effect. High inductive effect means the current flowing through this coil lags the applied voltage by an angle 90 degree. If it is not happening, because in coil always there will be small resistance. Due to this small resistance, you won't get this exactly 90 degree. That is phase shift. That is current should lag exactly 90 degree to with this applied voltage. Since this coil has some small resistance, we are not going to get this 90 degree lag. So, under that condition, what you are using is, you are going to use that copper shading band. This copper shading band will adjust the angle, that is the current and voltage. The angle between current and voltage is equal to 90 degree. So, for that purpose you are using, since you are using to adjust this angle, this is also called it as, this copper shading band is also called it as, that is power factor compensator. Okay. This is how the constructional feature of the energy meter you are going to consider. Now, you see this, how exactly this is arranged in this manner. See here, the supply is given to this current coil and voltage coil. See here, this is the magnet. There are two magnets you are using. Okay. So, this is called it as shunt magnet, and this U-shaped magnet you are going to call it as, this is series magnet. Okay. So, here the current coil is arranged in series through this load. You see that the current coil is connected in series with the load, and here the voltage coil is connected across the load. You see that in this, the one terminal of this phase is connected to this, and then you see that the other end of the coil, so it is connected to neutral, means the pressure coil is connected across the load. This current coil is connected in series with the load, means here this current coil is indicating the current flowing through the load, this potential coil is indicating the voltage across the load. So, here we are using this copper shading band. Okay, it is connected here. You see that copper shading band. Here that light aluminum disc is there, and then to control the speed of this disc, you are using this brake magnet. The torque produced due to the current flowing in the air gap of this brake magnet, so it will control the speed of the magnet. Okay. So, now I will show you this, how exactly the energy meter looks like. You see, this is the energy meter, it's single phase energy meter. Here the reading you are going to get, here the disc is there, it is rotating in this. Okay. So, it is giving the reading in terms of kilowatt hour. Here you can read that reading. So, now you see that where is, this is your shunt magnet. Here the potential coil is wound in this, and then here there is a series magnet. The current coil is wound. As I already told you, here you are using that thick coil of few number of turns. Here you are going to use thin coil of more number of turns. So, this is the shunt magnet and this is the series magnet. So, now here the disc you are using, this is the aluminum disc. the current flowing through this shunt coil will produce the flux, and also this current flowing through this field coil will produce another flux. Due to the interaction of these two flux, the eddy current will be produced on this, and then due to these fluxes and also this eddy current, the torque will be produced. This will make this disc to rotate. Okay. So, the rotation of this disc is controlled by the brake magnet here. Okay. Here we are using that brake magnet of this shape. Okay. So, here this brake magnet is connected exactly opposite to these two magnets, that is a shunt magnet and series magnet. This brake magnet is used to control the deflecting torque here. Okay. And then and also this speed produced on this, the speed of the aluminum disc. Where exactly we are connecting that copper shading band? You see that here there is a copper shading band. This copper shading band is used to make, that is, the current exactly lags the voltage by an angle 90 degree. This is how the energy meter construction is there. Now you see that how exactly this energy meter is used to measure the energy. Okay. Due to this current flowing through this shunt field magnet and due to current flowing through this current coil, so what we are going to consider, this is connected across the voltage, that is the load. So, voltage terminals, so connected across the load means this is directly proportional to voltage across the load, and then since it is the series that is a coil, current coil is connected in series with the load. So, this will measure the current. So, voltage into current will give you the power. Now, how exactly you are considering the power consumed in particular time? That is due to the number of revolutions of this aluminum disc. Now, you see that how exactly we are considering that power into time. So, we have the driving system, moving system, braking system and registering system. So, we have that 4 systems in this. The driving system, as I already explained, it consists of shunt magnet and series magnet. Shunt magnet is pressure coil is wound on the shunt magnet, and then current coil is wound on the that shunt magnet, and here you are going to connect the current coil on the series magnet, and then pressure coil or potential coil you are going to connect on the shunt magnet. Since it is connected across, so this current is directly proportional to voltage. So, this current is directly proportional to IL. So, you are using that copper shading band to make, that is, flux lag the supply voltage nearly by 90 degree. So, by using that copper shading band, so you are making that to happen, that is, current lags the voltage by an angle 90 degree. It is in driving system. Now, what it is in moving system? Moving system, you have that pointer. So, here in the moving system, so you have that aluminum disc that is rotating, so within the magnetic field of this shunt magnet and the magnetic field of this series magnet. The moving system consists of light rotating aluminum disc mounted on a vertical spindle or shaft. The shaft that supports the aluminum disc is connected to a gear arrangement, what I explained already in this system. See this is the aluminum disc, it is connected to the spindle. The spindle is attached to this gear system. The time varying fluxes produced by shunt and series magnet induce eddy currents in the aluminum disc. So, in turn, the interaction between these two magnetic fields and eddy currents set up the driving torque in the disc. So, the number of rotations of the disc is therefore proportional to the energy consumed by the load in certain time interval. See here, power in certain time interval, that is power multiplied by time will give you the energy. It can be measured in terms of kilowatt hours. What the braking system will do, it has that small permanent magnet located exactly opposite to the AC magnets. The disc passes between the magnet gaps. The movement of rotating disc through the magnetic field consisting of the air gap that sets up the eddy currents. So, as I already shown in the diagram also, you see here there is a air gap between the disc and the brake magnet. So, that reacts with the magnetic field and exerts a braking torque. So, by changing the position of the brake magnet or diverting some of the flux, there the speed of the rotating disc can be controlled. We have to control the speed of this rotating disc. So, that is done by this braking magnet. This is called braking system. So, next this registering or counting system, that is the recording system. The registering or counting system essentially consists of gear train driven either by worm or pinion gear on the disc shaft, which turns pointers that indicates on dials the number of times the disc has turned. So, you are going to count that number of revolutions of that aluminum disc. The energy meter thus determines and adds together or integrates all the instantaneous power values, so that the total energy used over a period can be measured by using that energy meter. So, now in the working principle we have considered the two mechanisms, that is mechanism of rotation of an aluminum disc which is made to rotate at a speed proportional to the power. Another one is the mechanism of counting and displaying the amount of energy transferred. This I already explained that how exactly we are going to consider. The metallic disc is acted upon by two coils. One coil is connected or arranged in such a way that it produces the magnetic flux in proportional to the voltage, and the other produces magnetic flux in proportional to the current. The field of the voltage coil is delayed by 90 degrees using the elec coil, or otherwise you can use that, and also along with this you are going to use that copper shading band. This produces eddy currents in the disc, and the effect is such that a force is exerted on the disc in proportion to the product of the instantaneous current and voltage. A permanent magnet exerts an opposing force proportional to the speed of the rotation of the disc. This acts as a brake which causes the disc to stop spinning when the power is disconnected. So, what it has to do? It has to stop the rotation of the aluminum disc. So, this causes disc to rotate at a speed proportional to the power being used. That is, you are using in the mechanism, that is, when you are going to consider this rotating mechanism, you are going to consider the aluminum disc and also the brake magnet. So, next, based on number of rotations of aluminum disc. So, the mechanism, when you are going to consider this, the aluminum disc is supported by a spindle which has a worm gear which drives the register. The register is a series of dials which record the amount of energy used. How exactly it is going to do? The dials may be of the cyclometer type, an odometer like display that is easy to read, where for each dial a single digit is shown through a window in the face of meter. I told you this. Here there is a window for each digit. Here you see that. So, here you are going to read. It should be noted that with the dial pointer type, adjacent pointers generally rotate in opposite directions due to gearing mechanism. So, now I already told you the current flowing through the current coil, that is through the series magnet is excited. When the series magnet is excited, the alternating flux you are going to consider it is phi 1. So, and due to current flowing through the potential coil, you are considering the flux produced is phi 2. So, now since the current I1 is directly proportional to phi 1 and this voltage V is directly proportional to phi 2. So, what will happen here? Current lags the voltage by an angle 90 degree. This phase displacement of exactly 90 degree is brought about by adjusting the copper shading band. So, now phi 2 across the narrow gap between center and side limbs of the shunt magnet you are going to get. So next, the fluxes phi 1 and phi 2 induces EMFs in the disc which give rise to circulatory eddy currents. The reaction between these two fluxes and eddy currents produce the driving torque. This driving torque has to be controlled by the braking torque. So that's why you are going to use that brake magnet. So braking magnet is used to control the speed of the disc. So here TB is directly proportional to phi square N divided by R, where phi is the flux of the brake magnet, N is the speed at which the disc rotates, and R is the resistance of the eddy current path. See here, observe this, the braking torque produced is directly proportional to N, where N is the speed at which the disc rotates. Since this flux and R both are constant, this TB, the braking torque, is directly proportional to N. By altering the position of the brake magnet, the desired speed may be obtained. So now, how exactly you are going to consider that at the equilibrium condition? We know that the deflecting torque, since you are using that current coil and potential coil, the current flowing through the current coil is same as the current flowing through the load, while the potential coil carries current proportional to voltage. This average deflecting torque we are going to get, it is the product of voltage and current, that is TD directly proportional to average power. Since we are considering that AC circuit, this TD is directly proportional to VI cos phi, okay, and this TD is equal to K1 VI cos phi, where K1 is the proportionality constant for this deflecting torque. And we saw that in this case this TB is directly proportional to N. The braking torque is directly proportional to N when we are going to consider this TB is equal to K2 into N, where K2 represents the constant of proportionality of this braking torque. Under equilibrium condition, the disc rotates at steady speed N when the braking torque exactly equals the deflecting torque, when TB is equal to TD. We have this TB is equal to K2 into N, we have TD is equal to K1 VI into cos phi. So when you are substituting and then rearranging the terms, so this will be K2N is equal to K1 VI cos phi. Now I told you that the energy is the power consumed at particular time. The power equation in case of AC circuit is VI cos phi, multiplied by time will give you energy. So that's why you multiply T on both sides to this equation. Now it is K2NT is equal to K1 VI cos phi into T, okay, T we have considered here, okay. So now what will happen when you are going to take only NT in the left hand side? This is NT is equal to K1 divided by K2, that is V into I into T into cos phi. Since both are constant, K1 and K2 both are constant, we can consider it is one more constant, that is equal to K3. And we know that P is equal to VI cos phi. See the left hand side, it is number of revolutions multiplied by time, that is equal to constant K3 into VI cos phi is power multiplied by T. This PT represents the power consumed in particular time, that is exactly the energy of the circuit, okay, energy delivered to the circuit. The expression NT gives the number of revolutions of the disc in particular time, and the expression PT represents energy passing through the meter in time. Therefore, you can use this equation and the relationship to find out the energy that is delivered to the load or energy consumed by the load, okay. So this is how you are using the concept of this induction type energy meter to measure the energy in case of single phase circuit. There are so many meters to measure, that is the energy in 3 phase also, okay. So you have only single phase this induction type energy meter in your syllabus, so it is very easy to understand. So the mainly it has the current coil and potential coil, okay. So now this is due to the torque produced in the due to the current flowing through this shunt coil and the current flowing through this series coil, okay. So and then how exactly you are controlling the rotation of this disc by using this brake magnet. So only the concepts, this if you know this, how exactly you are going to connect the constructional feature of energy meter and the working principle. So, you have to show how exactly this Td is equal to Tb to generate, that is the number of revolutions multiplied by time. This represents the total energy consumed by the load. This is what the working principle of induction type energy meter. Okay. So, now you have studied in detail the dynamometer type wattmeter and the induction type energy meter. In the dynamometer type wattmeter, you are going to measure the power. There also you have the two coils, one is the current coil, another one is the potential coil. So, current flowing through the current coil is directly proportional to current flowing through the load, then current flowing through the potential coil is directly proportional to voltage across the load. So, that is why, so the reading you are going to get the product of the voltage and current, that will give you the power. Okay. In case of energy meter, the power consumed in particular time, you are going to get it as the product of number of revolutions multiplied by the time taken, that is N into T. This is how exactly you are going to measure the energy by using induction type energy meter. Okay. So, now what is the outcome of this study, the measuring instruments? So, now in the last class I explained to you that what are the different, the basic types of instruments, the measuring instruments, since we are considering that electrical measuring instruments, the measuring instruments used to measure current, voltage, power, energy, etc. we are going to consider it as electrical measuring instruments. And then we have considered that the primary measuring instruments and secondary measuring instruments. So, primary measuring instruments, we know that the calibration is not required, but for the secondary measuring instruments the calibration is required. Calibration means we have to compare the reading of these instruments with the standard values, or we have to consider that is the value to be measured or the meter to be calibrated with respect to the standard, that meter what we are going to consider in the standard laboratories. Okay. We have to calibrate the secondary measuring instruments. For primary measuring instruments, the calibration is not required. And in the last class I already explained that what are the different torques you are going to consider in measuring instruments. So, now you have studied in detail the these two types of meters, that is the dynamometer type wattmeter to measure the power and induction type energy meter to measure the energy. Now, after studying this measuring instruments, what you are able to do, you can list different types of meters, that is the meters used to measure the current, voltage, or from the fundamental if you are going to consider, you are going to use that primary instruments and then secondary. In that secondary instrument, depending on the classification of the effect, that is heating effect, magnetic effect, you have considered based on the nature of that usage, you have considered different types of meters. So, you can classify, okay, you can list different types of meters, and then you are able to explain the construction and working principle of dynamometer type wattmeter, and you are able to explain the construction and working principle of induction type energy meter. Since our system is that outcome based, so now you can, these are the outcomes of learning that measuring instruments in module 2. Okay, all the best. Thank you.